I'll tell you who I am in just a second. The title of my deep dive today is really about thermal ALD. It's a bit of a grandiose title because I'm really not good at coming up with titles. So please don't read too much into, past, present, and future stuff. But we'll have a fun journey today nonetheless. Okay, so as I mentioned, I'm with Forge Nano. I'm the director of R&D for wafer applications there. I have a strong background in synthetic chemistry, BS from UW, doing organometallic catalysts, and then did my PhD at Illinois Institute of Technology, where I did ALD precursor discovery, which those two things are surprisingly similar, believe it or not. After that, I did a short postdoc at Argonne in, of all things, fundamental battery research. And then got an adult job working for Lam Research, where I did, sort of N+2 discovery for, for a range of applications on a range of tool sets. It was pretty fun working there. I got to sort of expand my horizons beyond just ALD into, electroplating and CVD, the meaner older sibling of ALD, as well as, etch and some other fun stuff. About 3 years ago, I came to Forge to focus back again on ALD. Again, I work in the R&D group, so we do a bunch of stuff beyond semiconductors. But today you get to hear my spiel about that. And just for context, I've been doing ALD for about 13 years, so a bit of time, nothing like Professor Parsons, but I've got a good start. So just briefly, I just kind of assume that nobody here really is too familiar with Forge Nano. So I'll just give a quick little synopsis. We're a small tool manufacturing company just north of Denver. We really focus on atomic layer deposition. We've been around for about 12 or 13 years, and the company sort of cut its teeth doing ALD on particles or powders, which, when you compare that to a wafer, is actually significantly more challenging for a range of reasons that we don't have time to go into today. And about 3 years ago, we acquired some really advanced semiconductor processing technology. So that's sort of where I came in and where this all fits together. Excuse me. We've been growing quite quickly. We're about 110 people now. We have about a 65,000 square foot facility. I finally convinced them to build me a class 10, class 100 clean room. So I get a new playground coming up in about a month. Really excited about that. We're primarily VC backed right now. We have about 100 million or so. Here's a small cross section down here at the bottom of our investors. We are looking to become profitable and take our company in a larger direction, which should be coming pretty soon. Here's a brief timeline. Some of the numbers don't exactly match up. Here it says 90 million and 120 employees. I don't know what's right, but marketing gives me these slides, so grain of salt there. Just a quick rehash. This is when we were founded. We got a lot of progress due to grant money from the Department of Energy, but there's some sort of pretty big milestones with like the scale of powder ALD. And we focused a lot on lithium-ion battery development because ALD can be used in a range of ways to improve that technology. But I want to point out sort of two things here. Number one, in 2020 is when the three ALD companies in this area sort of merged into one. One was ALD Nano Solutions, which also did a lot of powder ALD. And the other, and perhaps more importantly to my talk today, was Sundew Technologies. So this was started by a man named Ofer Sneff, and he developed a very advanced wafer coating ALD tool. So we kind of brought everybody together in one big happy family. But when I talk about the technology, it's based on this work from Sundew. These last two bits here are a bit important because it talks about a spinoff called Forge Battery and the installation of a megawatt hour prototype line here in Thornton in Colorado. But we just made an announcement today where we have a facility down in North Carolina to do gigawatt scale lithium-ion batteries. And we just got a $100 million grant from the DOE to expand that capacity to 3 gigawatt per year. So we're pretty happy about that news. I think my bosses would string me up by my toes if I didn't mention it. Okay, so what do I do? I've just talked about all this other stuff that Forge does. But really, I live in this process development column. We at Forge, we really care about, equipment sales, selling ALD tools, and of course, servicing and repairing those tools as needed. But in the R&D lab, I work in process development. So what that means is sort of I either talk to customers and see what struggles they have with their wafer applications, and try and see if we have a solution already ready or if we can develop one easily. Of course, I also get to sort of play in the sandbox a little bit and come up with brand new ideas for problems that might not exist yet. Again, since I'm a chemist by training and sort of the precursor expert on site here, I also get to play around with novel precursor chemistry, which is quite near and dear to my heart. Okay, so that's just all preamble. Here are the 4 things that I want to talk about today. I don't want to assume that everybody understands how ALD works, so I'll just briefly and very surface level go over that. And then I'll talk about, why ALD isn't used more. I think it's a very elegant technique that has a lot of very useful applications, but there are some significant drawbacks that I think most people are aware of. And of course, how Forge is trying to get over that. And then, I kind of want to compare and contrast ALD over plasma enhanced ALD, which is a bit more common in the 300 millimeter space, and then talk about some possibilities. Okay, so, if we maybe start on the right here, I usually talk to a lot of people about ALD. Not everybody has a background in it, but in the 300 millimeter space, ALD has been around for quite a while. So here's a bit of a timeline of how it's been used. For my money, the most important thing here was in 2007 when Intel announced to the world, hey, ALD is good enough as a high volume manufacturing production technique to be used in our high gate metal gate dielectrics when they went from the 65 to 45 nanometer node. I think those numbers are correct. I'm not a historian. I was a bit young back then, so if those are not exactly correct, I apologize. But the point is, this sort of announced to the world that ALD is a high volume manufacturing technique. I'm sure you all remember at that time, Intel was sort of the standard for consistent manufacturing. So it was pretty, from a ALD history perspective, that was quite a high watermark. So now if we sort of switch back to the left-hand side here, I'll get to talk about this little schematic here that we love to show in the ALD world, just in sort of how it works. Now remember, ALD is a vapor phase technique, right? So it's really in the same class as chemical vapor deposition, but it's kind of specialized. So if you imagine it as like a Venn diagram, CVD is this giant circle, ALD is like a smaller circle inside of that. So another way to think about that is all ALD is CVD, but not all CVD is ALD. So what makes that differentiation? Well, it's the surface chemistry. It's self-limiting surface chemistry, to be specific. With CVD, it's not self-limiting. There's a few different mechanisms there we don't really want to go into. So what that looks like sort of pictorially here is you start with a surface that has some reactivity. You have these sort of blue divots here. You bring in a precursor that has a reactive species that will react with that site. And you get one, in best case, you get one monolayer of precursor. So now you have these little spikes on the surface. Those spikes are unreactive to the incoming spikes, right? Metal doesn't want to react with itself. So you can keep putting in more of this precursor without growing more film. You then have to purge away the remaining metal and the reaction byproducts. That's the one, as a chemist, this little Lego block schematic sort of hurts my soul because this doesn't show you the reaction byproducts, which can be quite important. So those also need to be removed. That purge part of the cycle actually takes a bit of time, which is one of the reasons that ALD is so slow. And then you have to introduce a complementary precursor, these sort of blue bow ties here, that again react only with those blue spikes. And then you get, sort of that same monolayer coverage. Typically, this is, some sort of oxygen source or nitrogen source. So if you think about this as water, it's really hard to imagine water growing on top of water unless you're doing condensation, which we're hot enough, so we don't have to worry about that. We've now done one cycle of ALD. We get a digital amount of film, so the same amount of film, usually on the scale of angstroms or even sub-angstroms. You repeat that cycle as many times as you need to get your desired thickness. So one of the things that's sort of hidden in these Lego blocks is we're making and breaking surface bonds. That means our adhesion of the ALD film to the surface is dictated by the strength of those bonds. So that means you get really high adhesion. This self-limiting growth nature is where that perfectly conformal idea comes from, which is, I think, the most common aspect that people think about with ALD. The sort of asterisk there is if you wait long enough, if you're getting the species to where it needs to go, then you'll actually do conformal film. So this is a non-line of sight technique. It provides quite a high quality of film. And I just want to say, if people have questions, you don't have to wait till the end. I'm happy to stop and answer as we go. I wanted to put this slide in, not so you all can listen to me read, but because it could be a good sort of reference for people as
Matt,
making slides. Yeah, looks like Alan.
You asked for questions, so you're getting them.
Al, I'd love the immediate feedback, please.
This is Alan Diebold. Anyway, just a question from what I've read about ALD. You don't always get a perfectly uniform growth pattern. Sometimes you get hills and, or one area gets more growth than the other. And it's also my understanding that the first few layers, it takes a while before you get this layer after layer growth. The first part of the deposition is often doesn't go as easily as the rest of it. I wonder if you could comment on that.
Yeah, those are great points, Alan. Those are some of the dirty secrets of ALD, but I will say it also depends. There are processes that start with that ideal growth right away. It really depends on the surface. So now if you think about this from a surface chemistry standpoint, think about what a bulk film looks like. Let's use aluminum oxide, for example. Once you're growing on aluminum oxide, that will look the same with each half cycle. You're doing the same half cycle reaction, or you're doing proton transfer. It's quite basic. But if you think about a different incoming surface, let's think about just a silicon wafer. Now your surface is a native oxide silicon. That will look different than an aluminum oxide growing surface. So even there, those first few cycles will look different because of, let's say, hydroxyl density. Now let's go a little bit more complex. Let's think about a metal film, excuse me, like we'll use maybe a stark example like lithium. Lithium is extremely reactive. When it sees the metal precursor for aluminum oxide, trimethyl aluminum, it actually does uncontrolled growth. It does CVD until you coat that aluminum, right? So it really depends on the incoming surface. So that's sort of the first thing that to maybe answer your second question first. Your first question about the uniformity of how ALD grows, again, that really depends on the incoming surface. This is really what we like to call the nucleation behavior of an ALD process. And again, that's highly dependent on the surface. Another thing to consider is a lot of wafer flows have some etch process before you get to your deposition process. That can leave behind residues that don't matter for PECVD, but will matter for ALD. So if you think about leaving behind some fluorocarbon, maybe even just a single monolayer on a trench, that will inhibit ALD growth because it doesn't want to bond to that necessarily. It wants to clean it out, and then it has to find the surface to bond to. So again, it really depends on the incoming surface, and also, of course, the features. Looks like we have another question. Oh, go ahead, Alan, please.
Just thank you.
Of course.
A very simple question, Henning, from Intel. On the previous page, you talk about pulse A and pulse B. Why is it called a pulse?
Purge?
Pulse, P-U-L-S-E.
Oh, pulse. Oh, a pulse. Yeah. That's just common terminology. You can call it a dose. You can call it precursor introduction. Yeah, I mean, it's the terminology is quite fluid there. I will say, though, that a lot of typical ALD tools are what are called laminar flow tools. So you end up getting these nice laminar flow lines of your gas, and you sort of send through like a wave front of precursor and purge. So it's almost like you get a pulse of precursor and a pulse of purge. That is sort of where that, loosely speaking, if I kind of hand wave that's how I think about it, explanation.
And what is used as the purge?
Usually it's some inert gas. Typically it's nitrogen. And again, we're at temperatures that are usually below 400 C. So nitrogen's quite unreactive at these temperatures.
Thank you.
Yeah. But again, if you're doing plasma enhanced ALD, things can get a little challenging. But again, we won't go into that now.
Can I say something here?
Please.
So I just wanted to answer the question, why is it purge? There is a recipe in which the purging itself may have a composition of gases. It's typically inert gases, nitrogen or something, as you mentioned. So the timing and the gas that is used to purge are very important, and they determine the stepwise growth, because the ALD is a surface limited reaction growth. That was all the comment.
Yeah, appreciate the context there, Shankar. Thank you. Okay, so maybe looks like we're good for questions. I've already talked about the conformality nature. One thing that I haven't noticed, but it is quite important, is you get a uniform pinhole-free film at a very thin total thickness. And again, to Alan's point, in the ideal situation, right? So typically with oxides, we're talking within a nanometer or few. Now, if you talk about metals, there are other things at play here. So again, this is quite dependent. But normally, if you think about like why Intel adopted hafnium oxide as a high-K dielectric, it was because you got a uniform film without pinholes at quite thin total thickness. So that is, typically speaking, one of the benefits of ALD. Okay, so far I've only talked about thermal ALD and not plasma-enhanced ALD. So again, I'm a chemist, so I don't want to maybe talk out of turn here or maybe, then denigrate plasma-enhanced ALD. But from a surface chemistry perspective, plasma-enhanced ALD is normally used as a larger hammer. And really, for my money, ALD is a very elegant surface chemistry technique. So let me just kind of walk through some of the differences between PE-ALD, plasma-enhanced ALD, and thermal ALD. So if we look at our little table here with the red and green, ALD at some point your conformality will struggle. What that point is will depend on your plasma species. But with thermal ALD, as long as you don't have a high CVD component, you should maintain conformality. Of course, with deposition temperature, though, you can really reduce your deposition temperature with plasma. Right, you're putting more energy in through a different mechanism. But with thermal ALD, to sometimes get that same quality of film, you need a higher temperature. But here's another trade-off. You can damage the incoming surface with plasma, right? That's well known. So you have to be very careful how you start your ALD growth, especially since it's so thin per cycle, right? And I'll talk about a little bit more of that on the left side here. But with thermal ALD, the chances of that are pretty much zero. So one of the cartoons that we like to draw here is with plasma-enhanced ALD, once you get to a certain aspect ratio, your film thickness will degrade. Now you might have thick film on the bottom, if you're using ions, if you have a directional aspect. If you're just using radicals, then this will go away as well. But of course, with thermal ALD, this is conformal. The one thing though that is sort of lost in this analogy is it doesn't capture the composition of this film as you're losing thickness. In my experience, what typically happens is at some point, your composition will start to degrade before your thickness will. And that's simply because you don't get enough radicals or ions on the surface to densify the film, right? So those species are what are required to do the conversion. With thermal ALD, it's not limited, by that same respect. So, there's a lot of examples, especially with metal films, where once you get to about 10-to-1, the aspect ratio starts to really struggle. Now with oxides, oxygen radicals live a lot longer so that you get a lot more runway. But I'm sort of setting up later that, we'll talk about metal films. And so here's some examples of where we think this will really kind of play in. Okay, so I just want to drive home this a little bit. Hopefully it has be a little bit more clear here. This is that same sort of cartoon with a little bit more context. This is taken from this wonderful review on plasma enhanced ALD. So you lose these plasma species due to either directionality, recombination, or redeposition if you have ions. And here's one thing that the PE-ALD community has done a wonderful job of positioning what would typically be thought of as a bug into a feature. So one of the things that people have shown is if you use ions in plasma enhanced ALD to densify the sort of horizontal aspects, you can do what they call topographical ALD, where this sidewall is really low density because it's not getting densified by those ions, and then you can etch it away. Now that's great if you want that. But if you want an ALD process that looks like this, you're not going to get it. So, again, here's sort of what I was speaking to earlier, where the density, is different on different parts of the of the feature. Looks like we have a question from Robert.
Yeah, but so you comment on the non-uniformity of density. How about chemical composition?
Those usually go hand in hand. That's a great point. I like to think about it as stoichiometry. Another way to think about it is impurity content. So typically when people talk about plasma enhanced ALD, they say, oh, you need PEALD to reduce, impurity content, which is stoichiometry and then relates to the density, right? So what they don't take into account is how that looks on the sidewall, right? So to your point, like one would expect the composition to degrade, stoichiometry to degrade as you go down the feature. Shankar, looks like you have another comment or question there, bud?
Yeah, the question I have is, memory typically has a 10:1 aspect ratio or even higher compared to logic.
Sure.
Do you have a rough idea of how much is ALD used in the memory versus logic?
Yeah, I mean, from my understanding, there's a pseudo ALD process for tungsten, tungsten metal specifically, that it sort of blends the CVD ALD regime where they get a uniform enough deposition to do it. But there's not a lot of places. It's in logic, it's the gate. Sometimes it's used as a copper diffusion barrier, like tantalum nitride. So
Yes.
a little bit more common there. And I think to this reason.
Okay, thank you.
Yeah. Wow, it's already 8:30. Okay. Okay, let me see if I can talk a little bit more quickly here. So I love ALD. I've been talking about how great it is, but the main drawback is it's slow. You get great step coverage, but the deposition rates, even for the fastest processes, 1, maybe 10, TMA water, the sort of typical ALD process, you can get to maybe 10 nanometers a minute, but really that's in a very specific situation. So normally it's considered to be very slow. We've been told that once you get to this 10 nanometer per minute mark, things become a lot more interesting. So that's the first thing. The second thing is ALD tends to waste a lot of precursor. I think I saw a press release from ASM saying they have a metal oxide ALD process that was up to 50% efficient in precursor use. That means you're pumping 50% of your precursor down the drain. Still not very good. It gets even worse when you talk about metal ALD. So here's a typical precursor for platinum metal ALD. It's quite expensive, and normally you utilize maybe 10% if you have a really good process. So if you're flushing $225 per gram down the pump, that's not a very production-worthy process. So again, these are the most well-known. I'm not really blowing anybody's mind here. So in my opinion, the main reason for this is when you run ALD, you have to choose a pressure regime, either high pressure regime where you use precursor more efficiently, or a low pressure regime where your purge is more efficient. And if you think about this from a gas residence time, at the higher pressure, the precursor molecules move through the reactor more slowly. Those diffusion path lengths from your laminar flow lines are quite simply larger, and it's easier to get a uniform ALD film. But it takes longer to move precursor molecules out of the chamber because of that gas residence time. So if you want to move faster, you go to a low pressure regime. And this is typically how it's done in the 300 millimeter space. And you just deal with those extra precursor inefficiencies, which is why that 50% mark from ASM was such a, oh, that's kind of impressive. So people in the ALD world know this. And they've done a lot of strategies to maybe overcome this. One is to simply put more wafers in a reactor, go to a batch tool. So here you have 25, 50, 100 wafers. And there are some engineering challenges there, but people have overcome those for the most part. So you can actually improve your throughput with a batch tool. But the biggest downside is if something goes wrong and you have 100 of your wafers in that tool and you push stop, that's a big oops, right? You're scrapping a lot of expensive product. So, typically in the 300 millimeter space, people prefer single wafer. I always say 300 millimeter because right now Forge is focused on the 200 millimeter, just to sort of bring that out here. The other thing that people do is what's called spatial ALD, where you're either moving the substrate or moving the deposition head. That hasn't been adopted in the 300 millimeter space, and I don't really see a path to it directly. But again, that's a whole other talk. So again, I think for my money, you have to think about a single wafer solution to these problems. And so here I'll briefly talk about how our technology at Forge is differentiated. And it really comes down to three things. We have different hardware, proprietary fast pneumatic valves for introducing the precursor. Second, we have a unique reactor design, which we call the synchronously modulated flow and draw. I didn't come up with a name, so maybe just call it the SMFD. And then third, and again, I'm quite biased here, we are trying to use surface chemistry to catalyze reactions instead of just using that bigger hammer of plasma. And so let me just briefly step through these, and then maybe we'll get to some more examples. So here's what our fast pneumatic valves look like. If you notice that they don't have those VCR stubs on either side, and that's very intentional. Those VCR stubs are extra dead space that need to be purged with each half cycle. Quite simply, the more precursor you put into a chamber, the longer you have to purge. That's always the slowest step in the ALD cycle. So the more you can minimize that dead space, reduce that amount of precursor in the chamber, the faster your purge time is going to be, plain and simple. These are made of primarily stainless steel. We can heat them up to 200 C, but what makes them unique is how fast we can actuate. Single direction, we can do about 1 millisecond. The full on-off is about 3 milliseconds. I use these in my lab, and we have recipes that run at 3 milliseconds quite reproducibly. These have also been running in a Department of Defense 200 millimeter fab for the past 12 years. And we know how reliable they are. They're actually quite reliable. One just brief story, if you all will indulge me. When we were designing when Ofer was designing the reactor, he used off-the-shelf valves and found that he couldn't purge as fast as he expected to. So then he went back and designed these valves to take full advantage of the reactor design. So really, these by themselves, they're great, but they won't get you as fast as you need to go. They really work in tandem with the reactor design. Again, SMFD. Now, so I'll just briefly walk through what this looks like. It's a shower head design, a single wafer pedestal. We have, pump below the pedestal. We encapsulate the deposition zone with what we call a draw control or a gas curtain. So that draw control is a bit of a unique thing. Let me just sort of briefly talk about why that's special. When we turn this draw control on, as I'm showing on the left here, we're sort of holding precursor in the deposition zone. What we also do is artificially increase the pressure in that deposition zone. So if you remember back to my little slide earlier, this is that high pressure regime where we get to use precursor very efficiently. So, the other thing that's sort of hidden in here is this draw control is an inert gas, and there is some force pushing the gas back to the center of the shower head. So we get some turbulence. Now, normally turbulence in a laminar flow tool will completely kill you. You'll never be able to purge out those spaces. But because this is sort of a fake turbulent or pseudo-turbulent area, once we turn off that gas curtain, we hit our laminar flow regime just like that. We have a turbo pump, and we're constantly pumping on the chamber. So we're able to purge out extremely quickly, hit that low pressure state, remember the other state that I was talking about, extremely fast, and purge out very efficiently. So this was actually published in 2010. Ofer came out of Steve George's lab at CU, which is why he's in this area. So Steve put this in one of his reviews. Now, this is highly dependent on a lot of things. So this is a very simplified example. But just to kind of put some numbers on it, for some processes, we can get up to 80 or 90% efficient. For our slow processes, we introduce precursor for 50 milliseconds. But for, say, TMA water, we'll introduce TMA for 5 or 4 milliseconds. That draw control also helps us to keep some of that precursor off the chamber walls. So we don't have to worry as much about particle generation from the chamber walls, which is, a good thing for maintenance time and that sort of thing. When we talk about purges, this allows us to reduce our half cycle purge down below half a second, again, depending on the process. So that means we're switching from high to low pressure, pardon me, within each half cycle, right? So we have to do this twice each cycle. So really it relies on those FPVs. Now, we have a couple processes when you put all this together that have been running in a fab for, again, over a decade with a deposition rate over 12 nanometers per minute. And now if you think back to that earlier slide that I showed, where we want to get to a certain dep rate, that's pretty darn fast. Looks like I have another question from Shankar.
Yeah, so I mean, my understanding is it's not that much of turbulence as much as reducing residence time. Because if you have turbulence, your uniformity of the wafer will go kaput. And it's a big deal, especially on the front end, if you are using it for high K to have incredible uniformity across the wafer. So my feeling is it's not turbulence as much as getting the gas out. Did I get this right?
I can tell you we put a high K film with this technique with success. So one of the things, if you think about it, I think about it maybe slightly differently. This turbulence is helping us to circulate our precursor over that deposition zone, right? So, instead of having these laminar flow lines where the precursor is defined by those flow lines and the diffusion path lengths at the given pressure, this adds turbulence to that entire area. So instead of having localized hotspots dictated by those laminar flow lines, now you have a mixing of the precursor. Not only so you have like the laminar state and the turbulent state, you also get the transitions between the two. So you get to move precursor in ways that are quite unique. So, if you do this right, you can get a more uniform film. If you do it wrong, you are completely right and your uniformity will struggle. So it's all about knowing how to do this. And, we've been doing this for over 12, 13 years, so we have a pretty good idea. But so it depends on your turbulence. That's what I would say. Okay, great. So let me just talk about our catalysis briefly, because I think it's one of the areas that ALD really can be a differentiator. So again, we have another acronym here, and for that I apologize. When I refer to something as a CRISP process, it means catalyzing reactions for reduced surface process. You can just think of it generically as a catalytic ALD process. Okay. So maybe the best archetype for this is again work done by Ofer and Steve George back in the late 90s, where they showed that a nitrogen-based catalyst can help facilitate the formation of a silicon-oxygen bond. Now, just a little bit of backstory here on the life and times of silica. There's quite a large kinetic barrier to forming that bond. So fortunately, the whole field of catalysis, which has been around for a few hundred years, already had a solution. It was just a matter of applying that solution to surface chemistry, which has also been done. So, this really takes advantage of decades or even centuries of fundamental catalysis research to apply a very simple and elegant solution. Now, the key here is you have a non-metal catalyst. I want to stress that. There's a lot of metal catalysts, but we always focus on non-metals simply because if it does get left behind, having metal in your film can be a problem. I will say, though, that we have our silica crisp process. I've run it at temperatures from 85 C to 300 C, and I've done X-ray photo emission spectroscopy and haven't seen any nitrogen left behind. So one of the things that I like to sort of bring up here, when people say, like I mentioned earlier, that you need plasma to reduce impurities, you can use catalysis to do the same thing. Now, if you think about it from like a driving analogy, if you have a bunch of roads ahead in front of you, you have a highway that you want to go down and a bunch of dirt roads off to the side. What catalysis does is it closes off all those off ramps and gives you one road, that highway, that sort of keeps you on the straight and narrow. And that keeps, most of your impurities from coming in the film. So, again, I did catalysis as a younger lad, so it's I obviously enjoy it. One of the things that I've sort of talked about indirectly, James, I'll get to you in just a second, is, with this reduced impurity normally shows out as a higher film density, and then that knocks on to better film properties. So for silica, think about dielectric constant or breakdown voltage or leakage. All right, go for it, James.
Yeah, hi, Matt. I was just wondering, one of the areas that we're very interested in, this whole community is the application of digital twins. And I was just wondering if that's something that Forge Nano you are thinking about with respect to simulations of the catalytic, I guess, chemical reactions, then informed by measurements that you're taking.
This is actually why I'm here, to be because we're such a small company, we don't have a budget to do it ourselves. And now I think let me just briefly say there's two ways that I think that could be very valuable. Because we have that dynamic pressure change, I think modeling how the reactor behaves is the first step. And then, doing some DFT on potential reaction pathways of catalysis, that's the second thing. And we're working on both of those independently, but resources and
bringing
people
them together.
Bring them together is even a further step. Now, I have a lot of friends that do machine learning, and they really are excited for putting those two together to facilitate or accelerate that sort of development. So I also think there's a role for machine learning in this that we're sort of at the cusp of being able to take advantage of.
Excellent. Thank you very much.
Yeah, no, great point. So yeah, I'm going to mention a couple of brief things and then I'll move on. One of the things that we do differently is we prefer to include our catalyst with our conversion step. Instead of doing a 3-step ALD process, which now you have, an even longer cycle time, we try to combine the catalyst into the conversion step. So we now have still just an A-B, that typical ALD process. Because our valves move so quickly, I can finally control how many moles of catalyst and precursor I'm putting in the chamber. So one of the problems with catalysis is you can poison the surface. Because we have that fine control, we know where those limits are, right? So we know when we put in too much and we can dial it back and control them. One thing I didn't talk about that I'll just briefly mention is we control our precursor introduction by pressure. We don't use MFCs. So if we have TMA, let's say the room temperature vapor pressure is 9 or 10 torr, we'll bring that down to 8 or 9. To 4 or 5. So we can further limit the number of moles into the chamber. So again, we have sort of our flagship crisp process of silica. We have one for alumina, but to be quite honest with you, the TMA water process is so robust. It really only matters for this once you get below 110, 105 degrees Celsius. But we have it for other oxides. We're certainly exploring things that aren't quite as mature for nitrides, but I think there's a lot of potential here. And we do have quite a good metal film that takes advantage of this. Fortunately, I can't talk about the specific catalysts because that's sort of where our IP lives. Okay, so I've made it halfway through my talk, and it's already 8:43. Victor, would you like me to keep moving forward, or are there more important items to go over?
So we have a hard stop at 10:50, so we have 7 minutes. Okay.
Wonderful. I'll keep forging ahead. Pardon the pun. Okay, so this is the slide we showed before, but I wanted to populate it with our crisp process and how we like to think about it. Because those catalysts are just chemicals, thermochemicals, we retain that conformality. We now also access low deposition temperature regimes, so we can match or even beat what plasma enhanced can do. And we also don't have to worry about surface damage. I won't belabor the point here, so let's move on to that silica example. So here is how our silica crisp film compares with plasma enhanced ALD. Now I pulled this reference from the literature. I don't have a PE-ALD reactor on site, but this is a bit of a dated, I believe, an ASM tool. Again, this was published. Similar precursors, both at 250C. So we're a bit faster to get to 100 nanometers, but we use much less precursor. Again, they tell you what pressure they're using, what temperature. We know how long they introduce it for, how long we introduce it for. So we're like 66 times less. Sometimes that matters a lot for people. In silica, probably not, but in metal films, this starts to get a bit important. However, this next set are perhaps the most important ones to me. Our density is about 2.3. For this process, it was about 2.2. So we're more dense, which is great. If you look at the Ri, the dielectric constant, we're a little bit more ideal on both. Same leakage current at 2 megavolt per centimeter, but our breakdown voltage is higher. We've used this film on quite a few dielectric as a dielectric, including silicon carbide. And these, people always say your silica looks better than our silica. So this isn't something that we think is good. This is something we've confirmed with data. Okay, so that was the first example. The second one, and my personal favorite because it's the newest, is for a metal barrier seed application. So just briefly, what's a metal barrier seed? For those of you that aren't familiar, when you have an incoming feature, in this case it's silicon, and you want to put an electrical interconnect, you need to electroplate copper or some metal, right? Whatever your metal is. Unfortunately, it's very challenging to electroplate metal onto a dielectric. So you need some sort of adhesion layer. Now, typically you need an adhesion to your adhesion layer. So a typical solution is PVD, where your seed for copper is also copper, but you also have an adhesion layer for that copper with a Ti tungsten, just one example. Fortunately, that Ti tungsten is also a copper diffusion barrier, so it gets to play two roles there. In our silicon example, we also need a dielectric, so there's a thick silicon dioxide. However, we can think about using ALD for the same solution. Now, if you look at these two pictures, I promise you there are that same stack of ALD, but different composition. You just can't see it because it's, an order of magnitude or more thinner. So here what we've developed is a silica crisp process, a tinitride copper diffusion barrier, and a ruthenium, what we call a copper seed layer. So, if we just do a very rough comparison between the two, when you don't do your PVD correctly, you get voids at the bottom because your copper is literally pulling off due to the lack of adhesion. And you get narrowing at the top that leads to pinch off, and then voids, which will kill your device. So this pinch off here usually comes from either a thickness or resistivity delta from the top and the bottom. Now, those usually go hand in hand, so it's a bit of repetition there. But if you notice on the ALD side, this copper here, which is this big light colored material, that's uniform throughout the feature. These are only about 4-to-1 aspect ratios, but for PVD, you can do about 10-to-1 on a single side before it will no longer work. So this is sort of something that the field has just sort of lived with by thinning down the substrate. Now there's benefits to that, but there's also some extreme challenges. So what's stopping this from being a production-worthy technique? Well, it's really that ruthenium metal. Silica and titanium ALD solutions exist, but ruthenium metal is something that we've been working on. So here I just wanted to show just a little bit more details on it. I have shown you that there is actually ALD film here. The thicknesses don't really matter. This was done with cross-sem data that was not of proper resolution. But I also want to show that they did some etching here, some Bosch etching to make these features, so you get those typical scallops. The ALD film is conformal over those scallops, which is, I think, pretty cool to see. Again, very high quality. We've done this successfully on the 25-to-1 silicon vias and 10-to-1 through glass vias. We're testing even higher aspect ratio features, up to 50-to-1. Here's some information about the process. One thing I do want to say, though, is this whole stack can be deposited in about 2 hours, which is pretty darn fast for metal ALD. But again, that's the whole thing, the silica, titanium nitride, ruthenium. And we really haven't fully optimized the ruthenium process. We live in the 8-inch world, so keep that in mind. 8-inch uniformity looks great. Electroplates from side to side quite nicely. So I think we have a hard stop in 1 minute. So I think I'll probably leave off there instead of continuing on, or maybe I'll flash up. We just built a new cluster tool for the 200-millimeter space, so I'd be remiss if I didn't at least put it on the slides. We call this Tephra, and it's really designed to provide a solution for that metal barrier seed. So at that, I think I'll end and ask if there's any additional questions.
Thank you very much, Matt.